Ever wondered how to leverage pre-trained models in neural networks? Well, today we're going to explore the fascinating world of transfer learning. This incredible concept is transforming the field of artificial intelligence by taking advantage of pre-existing models to save time, energy, and resources when training a neural network. Imagine a world where you don't have to start from scratch every time you need to train a model. That's the beauty of transfer learning. It's like standing on the shoulders of giants, leveraging the work of those who came before us to reach new heights. This not only saves time, but also allows us to create more sophisticated models, even with limited resources or data. Transfer learning is like the secret sauce of the AI world, giving a significant boost to the efficiency of neural networks. It's changing the game, and it's here to stay. Now that we've introduced what transfer learning is, it's time to dive deeper into how it works. In essence, transfer learning is all about taking a shortcut. It's the clever trick of the trade in the world of artificial intelligence and machine learning. Picture this: you're a chef, and you've just made a fantastic tomato sauce. Now, you're planning to make a pizza. Would you throw away the sauce and start from scratch? Of course not. You'd use that sauce, add some cheese, and voila, you've got yourself a pizza. That's exactly how transfer learning works. It's about reusing a pre-trained model, which has been trained on a similar task, and fine-tuning it to perform the task at hand. This way, you're not starting from scratch. You're building on the knowledge that the model has already acquired. Now let's break this down a bit. In machine learning, models are trained by feeding them ample amounts of data. This data could be anything from images of cats to customer reviews. The model then learns patterns and features from this data, and it uses these learnings to make predictions or decisions. But here's the kicker. Training a model from scratch requires a lot of data and computational power and can take a significant amount of time. That's where transfer learning comes in. With transfer learning, you can leverage the knowledge from an already trained model and apply it to your new task. This can save you a great deal of time, computational resources, and the need for large amounts of data. Here's how it works. You take a pre-trained model, remove the last layer, which is responsible for making the final predictions, and replace it with a new one that suits your specific task. You then fine-tune this new model on your task-specific data. What you end up with is a model that's been tailor-made for your task, but without the hassle of training a model from scratch. It's like getting a head start in a race. You're not starting from zero, you're starting from a point of advantage. So, that's the basic idea of transfer learning. Now, how about we take a look at some of the pre-trained models out there? There are several pre-trained models available out there, and choosing the right one can make all the difference. In the realm of neural networks, a handful of pre-trained models have gained popularity for their robust performance. Let's dive into a few of these models, starting with VGG16. Trained on the ImageNet dataset, VGG16 is a convolutional neural network model that excels at image classification tasks. It's known for its simplicity and depth, with 16 layers that progressively extract higher-level features from the input. Next up, we have ResNet-50, another image classification champ. Unlike VGG16, ResNet-50 introduces the concept of residual learning to overcome the challenge of training very deep networks. It's a 50-layer deep model that uses shortcut connections to skip layers, thereby preventing the vanishing gradient problem. This makes ResNet-50 incredibly efficient and accurate when dealing with large-scale image datasets. Moving away from image data, let's turn our attention to BERT, a transformer-based model that revolutionized the natural language processing space. BERT, which stands for Bidirectional Encoder Representations from Transformers, was trained on a massive corpus of text data. Its strength lies in its ability to understand the context of words in a sentence by looking at the sentence as a whole rather than in parts. This makes BERT incredibly powerful for tasks like sentiment analysis, question answering, and language translation. So whether you're dealing with images or text, there's likely a pre-trained model that's a good fit for your task. Remember, the goal isn't to reinvent the wheel, but rather to leverage these pre-existing models to make your work more efficient. By using a model that's already been trained on a large dataset, you can save time and resources and still achieve excellent results. Armed with the knowledge of these pre-trained models, let's see how to implement transfer learning. Implementing transfer learning may sound complex, but with the right tools, it can be quite straightforward. Now let's dive into the concrete steps of implementing transfer learning using pre-trained models. First things first, we need to import the pre-trained model. There are many libraries available for this, but we'll focus on using Keras in this example. Keras provides a host of pre-trained models like VGG16, ResNet50, and BERT, which we can import with just a few lines of code. Remember, the choice of the pre-trained model depends on your specific task and the nature of your data. Once the model is imported, our next step is to freeze the layers of the pre-trained model. This is crucial because we want to keep the learned features of these layers intact. In Keras, freezing layers can be done by setting the trainable attribute of the model's layers to false. With the pre-trained model layers frozen, we can now add our new layers. These layers will be trained on our specific task data. Adding layers is a bit of an art and science both. While it depends on the problem at hand, a common approach is to add a few dense layers followed by a final output layer. Remember, the output layer's activation function and the number of neurons should align with the nature of your task. Now comes the exciting part, fine-tuning the model to our specific task. Fine-tuning involves training the model on our data. But wait, haven't we frozen the layers? Yes, we have, but only the layers of the pre-trained model. The new layers we added will be trained. This process allows the model to adapt to our data while leveraging the learned features of the pre-trained model. Fine-tuning typically involves experimenting with different configurations. You may need to play around with the learning rate, the number of epochs, and the batch size to get optimal results. Don't be disheartened if you don't get it right the first time. It's all part of the learning curve. Once you're done fine-tuning, it's time to test the model. Using a separate test set, you can evaluate how well your model is performing. If the results aren't satisfactory, don't worry. You can always go back, adjust your layers, or tweak your fine-tuning parameters. Remember, machine learning is an iterative process. So, there you have it. These are the steps to implement transfer learning with a pre-trained model. We've covered importing the model, freezing layers, adding new layers, and fine-tuning the model. It might seem like a lot, but once you get the hang of it, it becomes a powerful tool in your machine learning arsenal. And that's how you implement transfer learning with a pre-trained model. But let's not forget to summarize what we've learned. We've covered quite a bit of ground, haven't we? Let's take a moment to recap the key points we've discussed to ensure they've settled into your understanding. First, we delved into the fascinating topic of transfer learning. Remember, this is a technique in machine learning where a pre-trained model is used as the starting point for a related task. This method is a game changer, allowing us to leverage the knowledge a model has gained from a large data set to enhance performance on a similar but smaller task. It's like standing on the shoulders of giants, gaining a head start by utilizing the knowledge already acquired. Next, we explored a range of pre-trained models. We discussed VGGG16, a model renowned for its simplicity and great performance, commonly used for image classification tasks. Then we moved on to ResNet50, a model that introduced the concept of skip connections to combat the problem of vanishing gradients in deep networks. And lastly, we took a look at BERT, a revolutionary model in the field of natural language processing, which understands the context of words in a sentence by looking at what comes before and after them. The importance of choosing the right pre-trained model for your task cannot be overstated. Each of these models has its strengths and is suited to different types of tasks. Selecting the right one can significantly enhance your model's performance. Finally, we walked through the steps of implementing transfer learning with these pre-trained models. We started with loading the pre-trained model, then we froze the layers we didn't want to train, and lastly, we added our custom layers to fine-tune the model for our specific task. It's a process that may seem daunting at first, but with practice it becomes second nature. And that, my friends, is the power of transfer learning in neural networks. Harness it well, and you'll be saving yourself time and resources while still achieving high-quality results.